Next, I'll be walking you through the advanced baseline. And the goal of this notebook is to dive a little bit deeper into the internals of TensorFlow. We will not be going too deep into TensorFlow, just enough to be able to solve this problem and also be able to solve similar problems and related problems like multi-class classification problems and stuff like that. Key takeaways here will be to understand how to use predefined architectures which have proven to give like really good performance, and how to use them and how to modify their heads so that we can classify for the number of classes that we need in our specific setting, and what kind of loss functions to use and how to optimize that, and so on. I will be skimming through most of the initial setup part of the code because that remains the exact same as what we saw earlier in the previous notebook. We will still be using the aircraft CLI to log in, set up the data sets, and make a submission from this notebook. And after exploring the data set a little bit, we will proceed to visualize it, where I again encourage you to explore and gain more insights on the data by performing different kinds of analysis and see where you can get more performance, or more like try to generalize the model a bit more if there's a lot of skew or bias towards certain classes more than the others. So visualization and analysis definitely helps with that. We've also added another visualization where we've taken combinations of different classes and how often or how frequent certain combinations appear compared to others. So in this case, 0, 1, and 3 correspond to classes 0, 1, and 3, which is ether, ketone, and ester. So a combination of a single molecule containing all three of them appears quite a lot of times, more than around 520 times or something like that. And we can see that some combinations appear way less than others. If we were considering trying to convert this to a multi-class classification problem with each combination as a separate class, and it might not generalize to unseen classes, so just bear that in mind. So getting to the first specific part that's specific to TensorFlow is the custom data sequence generator. So what it is essentially, sometimes when you're using data sets like image data sets or audios, or essentially things that can take up a lot of space in memory, you cannot just load them all at once into memory. You will run out of memory if you are running them on lower hardware or sometimes even on good hardware. So the data generator essentially circumvents that. And how it does is that you override two methods, the len and the get item, which can be called. I suggest you explore into what the len and the get item functions, the methods of a class, do when you override them. Essentially, len method, what it does is when you call len of an object or instance of the class, it will return whatever you're computing in this len method. And get item is essentially what you would do when you're indexing an array. So if you do array of some index, whenever you create a class instance later, let's say this is the class instance, you can then index it with an index, and that index will be passed to this method, and whatever happens here will be returned. So what we're doing here is, instead of loading all of the data samples into the memory at once, we are loading them batch by batch on demand. So whenever we want a single batch, we at least TensorFlow internally, when you pass it a data generator, it knows it needs to, for every epoch, it's going to go through batches one by one until it's done with all batches. It's going to take a particular batch given its index, get all the elements out of the batch by reading them individually. It's entirely up to you how you implement it. It's highly advised to just read them dynamically when you need to. It might cause a little bit of overhead, but you will not be limited by memory anymore because you will not be needing all that memory. And you load that into memory. Optimizer does a step on it after it learns, and then it's out of memory again, or a new batch is loaded in, and if it doesn't have enough memory, then garbage collection will take over and kind of clear the memory. That's essentially a way to circumvent the problem, like I said, of not having enough memory by dynamically loading separate batches one at a time into memory. So that's what the data generator helps with. Like I said, the only methods you need to override are the len and the get item. The len, so that the model, when it's trying to fit, knows how many batches there are, which is total number of samples divided, like full division by batch size, and we're going to get each item by batch essentially. And then we'll create instances of the generator. So we'll instantiate it with the train data frame and also pass it a reference to the directory where the images are so that it can be used internally to read the images dynamically. And we'll also specify what we want the pre-processed image size to be. It is by default 500 by 500, but you'll notice here that in the underscore get image method, which is called internally, we are processing the image. We are first converting it to grayscale, so a single channel. Then we are resizing it to whatever the target size is, which is specified over here and will be passed later on. And we will also be inverting the bits. Now, this is a bit interesting because uh, you might have noticed that in every image the backgrounds are mostly white and there are regions of black lines which draw the molecule. So what happens is when you're inverting the bits, the white gets converted to black and black gets converted to white. And this is kind of a micro optimization, and the reason for that is computers in general, at least libraries, are good at handling math uh, with a lot of zeros in it, or handling arrays with a lot of zeros in it. So sparse matrices essentially. And they are optimized to handle sparse matrices and speed up such operations. So instead of having quite a lot of ones and zeros in the regions where the information is, we are inverting that to essentially represent the same thing, except now it's a more sparse matrix. Libraries which are optimized to handle sparse matrices will have a better time at doing so. And then we will divide it by 255 because if you recall, there's an image in which the pixel values range between 0 to 255. So we're normalizing that to a range of 0 to 1. What we do is when you call the lane of the train generator of particular batch ID. So this is what I meant by indexing it. So when you give it a batch ID, which is 12 in this case, on the instance of the class, the get item method is called with that index that you passed in the brackets, the square brackets. And it returns a batch, and in our case the batch size has been set to 100. So what it returns is two elements. So it's a tuple of two elements, x and y, for a particular batch, and x is the images essentially with 100 elements in the batch, and each of them is an image which is 224 by 224 in dimensions, and it's a single channel image, so it doesn't have another channel after that. And the y is essentially the same 100 elements except their corresponding classes and their class one hot encoded labels. We will be building two architectures, or building one architecture from the ground up and making use of another architecture that already exists and just modifying it a little bit. So first we'll be looking at the better one, which is the one that already exists. So if you take a look at the documentation online, you'll find quite a lot of architectures in tf.keras.applications that are defined for you to use. And you have the option of using them with their pre-trained weights, or you have the option of just ignoring the pre-trained weights and just initializing them to random weights and just training from scratch. What we're doing in this case is we're creating a model, which is an instance of the ResNet 101v2 class. So that returns a standard TensorFlow model, except we can pass it a few interesting parameters. So one of those parameters is the classes, where we need to specify how many classes there are in our particular application, or since it's a classification problem. And we also need to we can also additionally specify what the activation function is going to be. By default, I believe it's softmax, which can be overridden to sigmoid, which is what we'll be using in this case because sigmoid is what we need to use in a multi-label setting. The reason for that is softmax calculates the probabilities of all of these individual multi-class labels, and they will all add up to one. But we don't want that because more often than not, we want quite a few of them to be one themselves. So we don't want them to add up to one. So sigmoid is a completely good choice to go with in multi-label settings, or the best choice to go with in multi-label settings. And in this case, we are not initializing it with the pre-trained weights. We are going to be randomly initializing it so we can just train it from scratch because it's a relatively simple problem. One very important thing to note is that when you're creating an instance of the model, you need to pass in the input shape. And this input shape does not include the batch size. The batch size is passed separately when you're trying to fit the model. But the input shape is what is other than the batch size. So 224 by 224 by 1 in this case, which is just a single channel. And that's very important because that lets like the first layer know what the image size is. And 224 in this case is what the ResNet was previously trained on. So that's just the size we went with, although you could experiment with other sizes as well if you'd like to reduce the size. Yeah, that's more or less what you need to create an instance of a model. I also do highly recommend trying to take a look at the model summary every time, because one very important parameter that's quite often not seen when people don't use the summary is how many trainable parameters there are and how many non-trainable parameters. And you'll notice that there are quite a few layers in this ResNet architecture. And scrolling through all of them, we'll see that there are in total 42 million parameters, and out of that, 97,000 parameters are non-trainable. So what do they mean by non-trainable? Uh, Whenever the optimizer takes a step and uh, the, the gradients are calculated, they are not back propagated to certain nodes or certain parameters in this case. So those parameters to which the weights are not backpropagated to, they are called non-trainable parameters, and they're essentially fixed at whatever they are. And why would we need something like that? Two reasons. One, if you are doing transfer learning, you already had a very good pre-trained model, you could freeze all the other layers except for the final layer and try to just leave the final layer as a trainable layer and everything else frozen. So that way you're not training what's already trained and you're not overwriting the weights there. You're doing is you're fine-tuning it to your application. In this case, we are not exactly fine tuning, and why it says 97,000 is we have some layers where there are no non-trainable parameters, or there are partial non-trainable parameters. For example, batch normalization is one such example where it learns the mean and the standard deviation of the previous output. So it really doesn't need any learnable parameters. It's not going to learn anything. So in that case, there are no learnable parameters. So that's what it refers to. If you are doing transfer learning, it's most likely going to be very few trainable parameters and quite a lot of non-trainable parameters. And just ensuring that we have all these layers are unlocked, which is they are trainable, we can start proceeding to the next step, which is compiling the model. And before you train it, you need to compile it with an optimizer, a loss function, and metrics optionally. So optimizer is the logic that actually, or the class that actually performs the backpropagation and the update of the parameters based on the gradients. And there are different algorithms which perform this optimization step, and we will be using Adam optimizer, and with a specific learning rate that we've set to 2e per minus 3. And you are encouraged to play around with the learning rate. The learning rate just adjusts how fast or how slow it learns, and a slow learning rate can take a long time to converge. A faster one can result in it diverging if it uh, jumps away from it where it's supposed to be. Visually, I mean, speaking about it in imaginative sense. Second thing, like I said, is the loss function. So this will be the function that we're trying to optimize for using the optimizer. And we are going to be making use of binary cross entropy. So to the loss function, you can give it an instance of a loss function, a loss method, or sorry, a loss class, or a string parameter given the name of the loss function itself, which you can find on their documentation. It's very well documented. So we are making use of binary cross entropy in this case because we are in a multi-label setting. And if we were not in a multi-label setting, let's say, for example, we were in a multi-class classification setting where each sample has only a single label associated with it and everything else is zero, then we would make use of categorical cross entropy. And finally, metrics is just a list of metrics that are there for your reference and just so you know how well it's learning. Because in most cases, even if the loss function is optimized, the metrics may not be that great. So that indicates how good your model is performing from your perspective. And you are allowed to pass any number of metrics you want. They all get logged both for the training and the validation data sets, as we'll see soon. One thing I do want to point out is that accuracy is slightly misleading in this context because accuracy is not implemented the way we would expect for a multi-label setting. For example, let's say there are 10 classes in total, and for one sample, sample A, there are 3 classes associated with it. let's say your model predicted 2 out of those 3 classes correctly, and it still would be counted as zero accuracy for that. So we don't exactly want that. So which is why we will be making use of Hamming loss in this case. But uh, in most cases, accuracy should be completely fine if it's just a standard multi-class classification problem. So training the ResNet, we will be calling the model.fit using the train generator, and we will also be passing the validation generator to the validation data parameter. The number of epochs will be set by you, and this is also something that you're encouraged to play with. Setting it to too many epochs means that your model will overfit to the train data set, and its accuracy and its performance in general on the test data set and the validation data set is going to be pretty poor. So you don't want to set this to something too high. You ideally want it to be something where the loss of both the validation and the train data set goes down and does not go back up. The batch size is entirely dependent on how much your memory can hold. Essentially, need to ensure that doing too many epochs can be harmful too. You could be smart about it and try to save the best model with the best validation loss or best validation accuracy, depending on whatever metric you want to look at. And that's one way you can circumvent the problem of training too many times, because that way you're choosing the best model regardless of how long you've been training it for. But I will let you uh, implement that and experiment on how to get that sorted. It's a well documented solution that should be available about. And now taking a look at building custom architectures. More often than not, you would really not need custom architectures, since pre-specified architectures are really good and they perform really well out of the box. But it is good to know how the layers are constructed and what are the different nodes in the layers and how they work together. And for that, there are 2 different APIs that Keras gives to us. One is a sequential API and the other one is a functional API. We won't be going too deep into what the functional API is, but what you need to know is that it's more flexible and will let you create like more complex architectures. Whereas in sequential, it's just one input and one output. Sorry, one input layer and one output layer. And you cannot have parallel layers in between or parallel layers for input or output. So if you wanted to predict do multiple tasks using the same network, you can't do that using sequential. But for our purposes, sequential just fits. It's completely fine because all we are passing it is in images, and we are expecting a class out of it. And uh, first thing to note is we will be using the layers that are given to us by keras.layers, and we will be using the con2d layer, which is standard convolution, with filters, which is the number of channels. Kernel size is the kernel size that goes around for every convolution operation. The activation function can be whatever you would like it to be. You can play around with that. And the input shape is very important for the first layer that you're adding to your model. So by default, it comes with nothing, and the first layer you add expects that there should be an input shape attached to it. And like again, input shape does not include the batch size. Regularization methods right here, max pooling and dropout and max pooling is just standard. Uh, Nothing special going on here essentially. That's what I want to say. And finally, after all the convolution operations, we have quite a few channels. So it's been probably compressed down to a tiny size. And after that, we can flatten it and we can attach it to dense layers. And finally, we will connect it to the final dense layer, which has the number of classes that we want. And the activation for that will be sigmoid and not softmax. Very important. Taking a look at its summary, you'll realize that, again, it has quite a few, there are very few parameters compared to the previous ResNet model. So that it's not going to be as good at learning too many features, but at the same time, it's having too many parameters can also make you prone to overfit. So you want to choose somewhere in between and ideal for your application. Uh, but these might not be the greatest, but these drive home the point. Non-trainable parameters in this case are due to the presence of batch normalization, and all the other parameters are trainable. In case you wanted to set them to non-trainable, all of these layers can be iterated through them, each one of them, like you can iterate through them like a list, and you can set their dot trainable flag to false. This is also well documented, and I encourage you to check it out. And the rest of the operations remain exactly the same. we will compile the model with the optimizer, the loss function, which remains the same, and the metrics. Again, I want to point out that accuracy is not going to be accurate in multi-label context, so you need to implement a Hamming loss, something along those lines, Hamming accuracy, which will be a little bit more indicative of how good your model is. And then training it, we will be training it for 20 epochs in this case, and it's not going to give great results right out of the box, but you can experiment with how many epochs you want to train it for. More often than not, any number between 20 and 40 should work fine, and you should get good scores, like really good scores within training within those ranges. These graphs may not be too accurate because these were not trained for too long, but ideally what you want to see is the train loss going down and the validation loss going down as well, and you don't want the validation loss to come back up, which is indicative of overfitting to the training set. That's what you're looking for, and you should have everything you need in front of you, and if you mess around with the hyperparameters, you should get some really good results without changing much of the code using the ResNet. Obviously, the custom architecture is not going to be that great. Finally, taking a look at the predictions on the validation dataset. If you recall, the validation dataset had 500 samples in it. So essentially, it's just 500. It's an array of the size 500 by 10 and 10 classes for each of the 500 samples. Then we will create predictions on the validation generator. So instead of calling the dot fit, because we've already trained it, we'll be calling the dot predict method. And you can pass it the dataset or a dataset generator, a sequence generator, and we can generate the predictions out of it. Using that, we can then visualize what the metrics are going to be like. So using these two cells, you can compare the approaches, or you can try to optimize your approach and try to get more out of whatever you're training a model for, and try to change your hyperparameters and get better performance. Finally, it's time to create a dataset generator for our test set and load that into the model.predict. So the trained model, that is, so that it can predict the predictions for on the test set, and we can make a submission to Aircloud. So we do include a template labels file, which is all the file names in the test set, but with all the labels set as 0. So submitting this is going to be valid, but you're going to get a 0 score. And we want to create a dataset generator out of this, call it the test data frame, and pass it a reference to the test images directory. Then we call the dot predict on the test generator, and we results in the test predictions. One thing I might have missed out on explaining is that these are predictions in the range of 0 to 1, and they're continuous values. So we want to discretize them to integers as 1 and 0 if they're above 0.5. So you can do that manually using np.var. It's completely fine. When you do that, you get left with a massive array of the size 1012 by 10. So 1012 samples, 10 classes per sample. You can convert that back to a data frame with the same image name column. So make sure your format is exactly the same as what's depicted here. And using that, you can make a submission to Aircloud using the cell below. That way you can compare your different approaches and see which one fared the best and which hyperparameters fared the best. And hopefully any other problem you have, you should be able to directly drop it in here, pre-process the dataset if needed, and these networks should take care of solving it.